All right, so let's take roll first. Right, today is the 14th. Okay, Bartram, Blair, Donnelly, I think, is available online. Elwell, Levingood, Miller, Sheffield, Sullivan, and Tillis. All right. So where did we stop the last time exactly? Did we do, hold on. I don't think we got as far as here. Did we do all of these examples? Anybody? Somebody? Did we do all of these? Oh, that's the first one? Okay. I kind of suspected, but I wanted to make sure. All right. So let's move on to the second one. And the second one is kind of important because, as you're going to see, there are some situations where an atom can have more than 8 electrons on its outer shell when you draw the Lewis structure. So for the second one, it is sulfur dioxide, right? So again, what we have to do firstly is that we have to determine the number of valence electrons. Sulfur will contribute 6. Each oxygen will contribute 6, and there are 2 of them. So that's a total of 12 for the oxygens. And then when you add the 6 and 12, you get 18 electrons, which is equal to 9 pairs. All right? So we put the sulfur in the middle and surround it with the oxygens. And then we put the bonding pairs, 1, 2. Then the non-bonding pairs around the oxygens, 3, 4, 5, 6, 7, 8. And then the remaining pair will go on the sulfur. So now what we need to do is calculate the formal charges. And just to remind you of that formula, let me write the formula up here. For formal charge, it is the group number minus half the number of bonding electrons minus the number of non-bonding electrons. All right? So the formal charge for sulfur will be 6 minus half of 4 minus 2. So that's 6 minus 2 minus 2. So that's plus 2. So there'll be a charge of plus 2 on the sulfur. And then we do the similar calculation for the oxygen. It's a group number 6 minus half of 2 minus 6, which will be equal to minus, let me see here, 6 minus 1. So each oxygen will have a minus 1 charge. All right? So basically what's going to happen, if you remember what we did in a previous example, this pair of electrons will come here. The consequence of that is that this negative charge will cancel out one of the 2 plus charges here. This pair of electrons will come here, and that negative charge will cancel out the other positive charge. So therefore, the final answer will become this. And that's it, all right? And I want to point out, as I said before, that in this case, if you examine the sulfur atom, you'll see that the sulfur atom has 2, 4, 6, 8, 10 electrons on its outer shell, right? And, that is something that you may not have expected because, of course, we talked about the octet, right? That atoms try to achieve the octet. Well, it turns out that there's some atoms that can have more than 8 electrons on its outer shell. And those atoms are located in periods 3 and higher periods, 3, 4, 5, 6, 7, all right? So any element in period 3 and beyond can have more than 8 electrons on its outer shell, but elements in periods 1 and 2 cannot, right? Elements in periods 1 and 2 cannot have more than 8 electrons on its outer shell, but elements in period 3 and 4 and so on can have more than 8 electrons on the outer shell. And there's a reason for that, which I won't get into right now. I'm hoping that we'll be able to get to it before the end of the semester, all right? And that's all I can say about that for now, okay? Any questions about this particular example? Any questions? Any questions? Okay, let's see here. The next example is silicon dioxide. So let me clear this. So SiO2. So silicon again will provide 4 electrons. Oxygen will provide 6 times 2, so that's 12. So the total number of electrons is 16, which is equal to 8 pairs. We put the silicon in the middle, and we surround it with oxygens. And then we put the bonding pairs. 1, 2, then 3, 4, 5, 6, 7, 8. All right? Then we calculate the formal charges. So let me start with the silicon. So silicon, the group number is 4, minus half the number of bonding electrons, which is half of 4, minus the number of non-bonding electrons, which will be 0. So therefore, that's 4 minus 2, that's plus 2. So the formal charge on the silicon here is plus 2. Whoops. Where is this here? Plus 2. And then now we do the same thing for the oxygens. Of the group number, which is 6 minus half of 2 minus 6 equals minus 1. So each oxygen will have a -1 charge. All right? And then now this pair of electrons will go here. This pair of electrons will go here because the 2 negative charges will cancel out the 2 plus charges. So the final answer would be double bond Si, double bond O. And that would be that. All right? Okay, any questions about that example? Any questions? No questions? All right, so let's continue our discussion. Oh, some other examples, okay. And these are important because these are polyatomic ions. All the examples that we have looked at so far were molecules, all right? So let's see how we deal with polyatomic ions. So let me go back to my writing pad here. So the first one is a nitrate, NO3 minus. So we do like what we did before, but we have to take into account the negative charge, right? So nitrogen will contribute 5 electrons. Each oxygen will contribute 6 electrons multiplied by 3. So that's 18 electrons. And because of the negative charge, what we have to do is that we have to add an extra electron. So for each negative charge that is present, we add an electron. And if it was a plus charge, we'd have to subtract an electron. So in this case here, it's 18 plus 1, 19 plus 5, 24 electrons, which would be equal to 12 pairs. So we put the nitrogen in the middle, and we surround it with the oxygens. And then what do we do next? What do we do next? Anybody? Well, oh, Sullivan is here. Make sure I get that down. Okay. So what do we do next? Anybody? Well, okay, so the bonding pairs. 1, 2, 3. What next? We have used 3 of the 12 pairs. So what next? Okay, so 4, 5, 6, 7, 8, 9, 10, 11, 12. What next? Okay, so let's do the formal charge for nitrogen. How do we calculate that? Anybody? How do you calculate the formal charge for the nitrogen and also for the oxygen? What's the group number for nitrogen? 5 minus half the number of bonding electrons. How many bonding electrons on for the nitrogen? Remember, each line represents a pair of electrons. Come on, folks. What's the number of bonding pairs around the nitrogen atom in this structure? And you guys out there in Zoom, you can also answer as well. Nobody knows how many pairs of electrons or how many electrons does nitrogen has? It would be indeed 6. You're absolutely right. And how many non-bonding pairs? 0. So that's 5 minus 3, so that's plus 2. So the nitrogen will have a plus 2 charge. And then in the case of oxygen, what would be the formal charge for oxygen? And remember, the calculation for oxygen can be focused on just one. It's the same as the others. Minus 1, because it's 6 minus half of 2 minus 6. So that's minus 1. So each oxygen will have a minus 1 charge. Okay, so what do you think is going to happen next? We have 3 negative charges, 3 oxygens with negative charges, all simultaneously bonded to a nitrogen with a plus 2 charge. So what do you think is going to happen next, based on what we did in the previous examples? So you're saying this? Well, I can understand why you say that, but that would be incorrect. Nope. Can anybody tell me why this would be incorrect? Because what she's suggesting is that this is what's going to happen. Right? But that would be incorrect. Can anybody tell me the reason why? Something I mentioned just a while ago. about the periods? What did I say about the periods? Exactly, because exactly. Nitrogen cannot have more than 8 electrons on its outer shell because nitrogen is in period 2. Remember I said that only elements in period 3 and beyond. So only one pair of electrons from the oxygen, from one of the oxygens, will form a double bond. So the final answer, oops, let me erase this here. Okay, so the final answer is going to be O double bond N, and then O minus, and you're going to have O minus here as well. Now, only one of the 2 plus charges will cancel out, so you're going to end up with a plus charge here. And that would be the final answer right here. All right? Okay, any questions about this example? Any questions? All right, so the last example on this page is the carbonate ion. So can I clear this? Okay, so carbonate. So I want you now to tell me the steps. CO3, 2 minus. How many electrons does carbon provide? Four electrons. How many does oxygen provide? 6, but you have to multiply by, so that gives you 18. And then we have the 2 minus charge. So how do we include that? If we have 2 negative charges, what does that mean? You have to have 2 more electrons, exactly. So the grand total is 24 electrons, which is equal to 12 pairs, right? We put the carbon in the middle, surrounded with the oxygens. And then we start off with the bonding pairs. 1, 2, 3. Then the non-bonding pairs around the oxygens. 4, 5, 6, 7, 8, 9, 10, 11, 12. What next? Formal charges. So let's do the formal charge calculation for carbon. How do we calculate that? Four minus half of 6 minus 0. So that's 4 minus 3, so that's plus 1. So there's a plus 1 charge on the carbon. And then for the oxygen, what's the formal charge? Minus 1. 6 minus half of 2 minus 6 equals the minus 1. So each oxygen will have a minus 1 charge. And then what? What's going to happen next? Like that, right? So you're going to end up with this. And that would be the final answer. All right? Okay, any questions about this one? Any questions? Any questions? All right, so let's move on. Back to the PowerPoint here. Okay, so I want to talk about this concept of polarity of bonds and how it's related to the electronegativity of the atoms that are involved. So we need to define electronegativity what it is, and it's basically a measure of the ability of an atom to attract shared electrons to itself, or bonding electrons to itself, right? So you have two atoms sharing electrons. The one that has the greater attraction for the shared electrons will have a greater electronegativity value, all right? And a guy by the name of Linus Pauling, he basically combined some properties, some data, thermodynamic data in relation to ionization energy and electron affinity, and he came up with a scale, a 4-point scale, where 4 represents the maximum electronegativity possible. And based on that, he was able to determine the electronegativity of different atoms or different elements. So as stated here, the greater the electronegativity of an atom in a molecule, the more strongly that atom will attract the electrons in a covalent bond. And what you'll find is that the trend is, in the periodic table, going from left to right, the electronegativity increases, and it also increases going from bottom to top of any group. So this is the table I was referring to, the one that is put forward by Linus Pauling, and it gives you the electronegativity values of different elements. And as you can see here, the most electronegative element is fluorine. Fluorine has a maximum possible value. And then you have others like oxygen, phosphorus, and so on. And the low values would be attributed to the elements to the left of the periodic table and down, all right? So of all the elements that are in existence, the least electronegative would be cesium and francium, all right? Okay, so this is a table that is also available in Canvas, and you can use this to do the type of calculations we're about to do. All right, so now this question is saying, referring only to the periodic table, give the order of increasing electronegativity of these sets. So basically, you're starting from the lowest to the highest, all right? So let's start off with A. You're given chlorine, magnesium, and silicon. So of these three, which would you expect to be the lowest? Remember now, electronegativity increases from left to right of a period, and it increases going from bottom to top of a group, all right? So let me see here. Chlorine is there. Magnesium is all the way to the left. And silicon is in between magnesium and chlorine. Okay. So which would you expect of these three to have the lowest electronegativity? Magnesium followed by silicon followed by obviously chlorine. All right, very good. Okay, what about B? Arsenic, nitrogen, and antimony. Okay, let me see. Where's arsenic? Okay, arsenic is there, and it is below nitrogen. And antimony, where's antimony? Oh, antimony is below arsenic. Okay, so which of these three would you expect to have the lowest value for the electronegativity? They're all in the same group, right? So which of those would have the lowest, starting off with the lowest? Antimony, SB, followed by arsenic, and then, of course, nitrogen. Okay, the last one, arsenic, selenium, and antimony. Okay, so arsenic is there, selenium is to the right of it, and antimony is below arsenic. Okay, so which would you expect to be the lowest in that series? Antimony would be the lowest, followed by arsenic, and then, of course, selenium. Okay, very good. All right. Enough of that. So let's talk about the different types of bonds based on the electronegativity difference of the atoms connected by that bond, right? Now, first, let's deal with a situation, the easiest situation, in fact, where you have two identical atoms bonded to each other, right? Like two chlorine atoms or two oxygen atoms. In that case, both of them would have equal attraction for the shared electrons because they're both identical, right? So basically, the electrons would be distributed between them equally. So basically, we call that bond a non-polar bond, or more specifically, a non-polar covalent bond. That's what this is saying right here, right? Or you can just abbreviate it NPC, all right? So in a non-polar covalent bond, basically the electrons are distributed equally between the two atoms sharing that bond. Now, if you have two different atoms where the electronegativities are different significantly, then obviously electrons will not be shared between those two bonds, right? So basically, we call that bond a polar covalent bond. And in this type of bond, the electrons would be attracted to the more electronegative elements. So polar covalent bond is where you have unequal sharing of electrons between the two atoms involved. And then now, if the electronegativity difference is very large, then it's so large that you have a complete transfer of electrons from one atom, the less electronegative atom, to the more electronegative atom, right? In that case, we're talking about an ionic bond, right? I'm just going to use I here to represent an ionic bond, right? So basically, as far as differences in electronegativities are concerned, these are the three types of bonds that you can categorize. You have the nonpolar covalent bond, where the electrons are shared equally. You have the polar covalent bond, where you have an uneven sharing of electrons because one is more electronegative than the other. And then you have the ionic bond, where the difference is so large that you have the complete transfer of electrons from the least electronegative element to the more electronegative element. So this is just basically a chart which gives you different types of bonds, and it basically indicates the different differences in the electronegativity values and whether or not they fall into the three categories I mentioned. So for example, the carbon to hydrogen bond is basically nonpolar for most intents and purposes. And that's because their values in terms of carbon and hydrogen is very small. If I remember correctly, hydrogen is 2.1 and carbon is 2. Let me see here. Okay, hydrogen is 2.1 and carbon is 2.5. That's relatively close, right? So even though they're not exactly the same, for most intents and purposes, we consider that bond to be nonpolar, all right? And then now when you get to something like carbon and oxygen, right? Let me see what the values are. So carbon is 2.5 and oxygen is 3.5. That's a difference of 1. That's more significant. And therefore, for most intents and purposes, we consider that bond to be a polar bond. And then now when you get to something like cesium fluoride, let's look at the values for cesium and fluorine. Where's cesium? Cesium is 0.7 and fluorine is 4. So 4 minus 0.7, that's what? 3.3? That's, that's definitely different. A difference of more significance compared to the others that we saw before. So that bond between the cesium and fluorine would be considered to be ionic. In fact, there's a criteria that is used to determine whether or not a bond is falling into any of those categories. So here are the criteria, right? In the case of the nonpolar covalent bond, if the difference is between 0.0 and 0.4, then we consider that bond to be nonpolar covalent bond, right? And some examples are shown here. Definitely the ones where you have two identical atoms bonded to each other, that is definitely nonpolar covalent. But even something like chlorine to carbon, chlorine to bromine, right? The difference is 0.2, right? Or hydrogen to silicon, the difference is 0.3. These are all considered to be essentially nonpolar covalent, all right? Then we have the polar covalent. Now, the criteria for that is that if the difference is between 0.5 to 1.7, all right? If that's the case, then that bond is considered for most intents and purposes to be polar covalent. And some examples are shown here. The oxygen to chlorine, that's 0.5 difference. The chlorine to carbon, that's 0.5 difference. And the oxygen to sulfur, that's 1.0 difference. These all fall within the range, and therefore, these are all considered to be polar covalent. And then now, the last category, which is ionic, where the difference is large. And when we say large, we're talking about the difference being 1.8 or more. Then we consider these bonds to be ionic. So for example, the bond between potassium and chlorine, that difference is 2.2. The bond between sodium and nitrogen, that difference is 2.1. And the bond between cesium and sulfur, that difference is 1.8. So therefore, we consider all these bonds to be ionic, all right? So that's basically how you can determine whether or not a bond is ionic covalent or, nonpolar covalent or polar covalent. Okay, now based on this, you guys, I don't have a copy of that assignment here, but let me see if I can bring this up. So let me get out of this here. Let me go here. And go here and files, assignment. Is it 9? I've lost track. Okay, right. So did I give you guys assignment 9? I didn't? I thought I did. Okay. And I don't think I have any copies of assignment 9 here with me. All right, so this is assignment 9 right here. And let me just help you with maybe the first two. It's very easy, actually, based on what we just learned in this table right here. Okay, so the question here is asking for you to determine the type of bond that will form between the atoms indicated on the left, atom 1 and 2, and use the electronegativity chart and the bond type chart to help you, right? So let's look at the first one, the first pair, arsenic and sulfur. So let me go to the electronegativity chart. Okay, so arsenic is 2.0 and sulfur is 2.5, all right? So that means that, get my writing. So arsenic is 2.0. Arsenic is 2.0, sulfur is 2.5, right? So the difference between them is 2.5 minus 2.0, right? So that will be equal to 0.5. So what does that mean? What type of bond is it? Is it nonpolar covalent, polar covalent, or ionic? Polar covalent, so PC. And that's it. That's basically all you have to do to complete that table, right? Okay. So when you get an assignment, make sure that you do these for number 1, at least based on what we have covered just now. All right, so let me get out of this here. In fact, let me clear this here and go back to the PowerPoint. Okay, so here we have some pictorial representation of different types of covalent bonds, nonpolar covalent bonds and polar covalent bonds, right? As we said before, in the case of two atoms that are identical bonded to each other, that bond will automatically be nonpolar covalent. So the electrons being shared between them will be equally distributed between the two hydrogen atoms. In the case of a polar covalent bond, such as the hydrogen to chlorine bond, as you can see here, there will be an uneven sharing of electrons between the two atoms, the hydrogen and the chlorine, all right? So that's what happens in the case of a polar covalent bond. Now, there are different ways of representing it. And if you look here, you see that we can show that this bond between the hydrogen and chlorine atom is covalent by using these symbols right here. And these symbols basically represent, in this case, a partial positive charge, and in this case, a partial negative charge, all right? So these are not full plus charges or minus charges. These are partial because the electrons are not completely transferred. They're shared, but shared unevenly. So we use this symbol here. This, by the way, is a Greek letter delta, right? So delta basically in this context represents partial, all right? So the hydrogen is partially positive and the chlorine is partially negative. Another way of representing the separation of charge is by using this arrow right here with a cross at the tail, right? And the convention that is used when applying this symbolism is that the arrow is pointing from the positive end of the bond to the negative end, right? So that's basically defined as the direction of that separation. And there's a term that is used for the separation of charge within a bond. We call this a dipole. So, I thought I had it typed here, but I guess not. So let me just squeeze that in somewhere here. So the term dipole you're going to see is basically the same thing as a separation of charge in a bond or molecule. All right? That's what a dipole is, right? So we can have a separation of charge in a bond, as we see here in the case of hydrogen chloride, but you can also have a separation of charge within a molecule. We're going to talk about that later on. Okay, so this question is asking for us to use the electronegativity values to arrange the following bonds in order of increased polarity. Okay, so I'm going to need your help here. I'm going to need you guys to refer to the table and tell me what the values are for each of these atoms. So what's the electronegativity value for bromine? 2.8. What's the value for chlorine? 3.0. And that will be 3.0 here. And that will be 3.0 here, right? And this will be 3.0 here. And I know fluorine is 4.0. And hydrogen is 2.1, right? 2.1. And chlorine is 3.0. What's the value for iodine? 2.5. And chlorine is 3.0. Okay, so we have to find a difference in each case. So for this difference here, that would be 0.2. For this difference here, that would be 0. For this difference here, that would be 1.0. This difference here would be 0.9. And this difference here would be 0.5. So the one with the lowest, because the question says here to order them in terms of increasing polarity. So the lowest one would be the chlorine to chlorine bond, followed by the iodine to chlorine bond, followed by the hydrogen to chlorine bond, followed by, no, wait a minute. I misspoke. My bad. Because the bromine to chlorine is 0.2, so that would follow the 0. So let me erase this here. My bad. That's my fault. Okay, so bromine to chlorine would be the next one after chlorine to chlorine. And then iodine to chlorine. And then hydrogen to chlorine. And then chlorine to fluorine. So that would be the answer. All right. Okay, any questions about this? Any questions? Any questions? All right. So I talked about this earlier, that there are some molecules where the octet rule is not allowed or not followed. We saw the example of sulfur dioxide, where the atom in the middle can have more than 8 electrons. But there are other situations where, for example, you can have a total number of valence electrons that would be an odd number. So therefore, one will be left out in terms of being unpaired. And whenever you have structures where that is the case, we call them free radicals, all right? You can also have some situations where the central atom will have less than 8 electrons. In other words, the octets would be incomplete. And then you have some, as we saw in the case of sulfur dioxide, where you can have more than 8 electrons on the outer shell. And we say that these atoms have what we call expanded valence shells, all right? And as I said before, those atoms would be in period 3, 4, 5, 6, and 7. You cannot have any element in periods 1 or 2 that have more than 8 electrons on its outer shell. Okay, so some more Lewis structures. And these are some good examples here. In fact, what I'm going to do is let me copy this here. And let me go to, you know what? Let me go to Word. Come on. Oh, here it is. And then let me do the draw thingy. Well, let me do this first and paste this here. Okay, so Again, our task is to draw the Lewis structures for these molecules and ions. So let me start off with bromine pentafluoride. All right. So first step, of course, is to count out the valence electrons. So bromine will contribute how many? 7. And fluorine will contribute how many? 7, but we have to multiply that by 5, right? So that's 35 plus 7, that gives you 42 electrons, which would be equal to 21 pairs, right? So we put the bromine in the middle, and we surround it with the fluorines. And I don't know if I mentioned this before. At this juncture, we are not concerned with the three-dimensional arrangement. We just want to make sure that we have all the atoms involved connected, right? So I'm just going to surround the bromine with the fluorine like this, Br. Okay. What's the next step? We have 21 pairs of electrons to play with. So what's the next step? Bonding pair. So 1, 2, 3, 4, 5, and then a non-bonding pairs, right? So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? So I've used up 20 of the 21 pairs. So the remaining pair would go where? On the bromine. And that would be the final answer. But of course, you need to calculate the formal charges just to be sure. So the formal charge of the fluorine will be equal to what? How do you calculate the formal charge of the fluorines? Minus, and that'll be equal to 0. So the fluorines will have no charge. And what about the bromine? Formal charge of the bromine, that'll be equal to what? Seven minus 10 minus, and that's equal to what? 0. 7 minus half of 10, 7 minus 5 is 2. Minus 2 gives you 0. So there are no charges, right? So that would be the final answer. All right? Any questions? All right. So let me get rid of this and do the next one. The next one is a sulfate ion. SO4, 2 minus. So S would contribute how many electrons? 6. And the oxygen will contribute how many each? 6. But there are 4 of them, so we have to multiply by 4. So that gives you 24 provided by the oxygens collectively. Then we have the negative charge. So what does that mean? 2 electrons, all right? So the total here would be 32 electrons, which would be equal to 16 pairs. Whoops. So we put the sulfur in the middle and surround it with the oxygens. All right? And then we put the bonding pairs. 1, 2, 3, 4. Then 5, 6, 7, 8. Why did I do that? 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, what next? Okay, so let's do the formal charge of sulfur. How do we calculate that? 6 minus half of 8 minus 0. So that's 6 minus 4, so that's plus 2. So the sulfur will have a plus 2 charge. And what about the oxygens? That will be equal to what? Minus 1. 6 minus half of 2 minus 6 equals to minus 1. So each oxygen will have a formal charge of minus 1. So what's going to happen from here? Only 2 of them, because you have 4 negative charges bonded to the central atom, which has a plus 2 charge, right? So only 2 of the 4 negative charges will cancel out. So you can, and it doesn't matter how you do this. You can do like this and this, and the final answer would be S double bond O, single bond O with a negative charge here, and a single bond O with a negative charge here. And that's it. All right. Okay, any questions about this one? Any questions? Any questions? All right, I'm going to leave the other 2 for you to look at. If you have any problems with doing those, again, feel free to contact me. But basically, it's the same idea that we have been doing all along. You count out the valence electrons, you arrange your atoms such that the central atom is in the middle. Usually the central atom is the single atom or the least electronegative atom. You put the bonding pairs first. If you have any more electrons left over, you put them on the surrounding atoms, with the exception of hydrogen. You cannot do that for hydrogen, right? And then you calculate the formal charges, and then if necessary, you make double bonds or triple bonds based on the charges that are bonded to each other, all right? Okay, so let me go back to the PowerPoint here. Okay, so we're going to talk about a very important phenomenon known as resonance. And for those of you who have to do organic chemistry, this will become very important, all right? So you'll be getting somewhat of an introduction here. Basically, you can have a situation where a structure, a molecular ion can be that differ only in how the electrons are distributed. But according to this theory, it's called the resonance theory. The resonance theory says that in that particular situation, the individual structures do not represent the true structure of the particular molecule or ion. Instead, the true structure is what we call a hybrid of the different possible Lewis structures, all right? A good example of this would be ozone, right? So what you're looking at here on the screen is one possible Lewis structure of ozone and another possible Lewis structure of ozone right here. And to get from one structure to the other, all you have to do, if you look at this carefully, is that this pair of electrons will go here to form a double bond here. And at the same time, this pair of electrons will go here. So the result would be a single bond here, right? As a result of that, you have the transfer of the negative charge on this oxygen ending up on the other oxygen to the right, okay? So basically, one could say that this represents the true structure of ozone or this, but in actual fact, according to the resonance theory, the real structure is a hybrid between these individual structures that you can actually draw on paper, right? So one analogy I like to use to explain this, which I'm probably sure you're familiar with. You may know, or you should know, that a mule is a hybrid between a horse and a donkey, right? So basically what that means is that the mule will have some characteristics in common with a donkey and other characteristics in common with a horse, right? Well, according to this theory, the real structure will have some characteristics of one possible Lewis structure and then some characteristics of the other, right? But it's a hybrid. And as I said before, this whole concept of resonance is very important because this is important in explaining certain chemical features of certain organic compounds, the type of reactions they undergo, whether or not they're acidic and basic and so on. So as I said before, for those of you who have to do organic chemistry, you're going to see this whole idea of resonance coming up a lot in organic chemistry 1 and 2. All right. Okay, so much for that. Oh, one thing I forgot to mention here. So as I said before, this pair of electrons will go here to form a double bond, and at the same time, this pair of electrons will go here. So according to the resonance theory, this lone pair of electrons here is basically delocalized, because what they're saying here is that this pair of electrons can be found here as well as found over here at any one particular instance, all right? And again, that will become important, as I said before, for those of you who have to do organic chemistry. Okay, so let me move on now to an example. Okay, so basically they're asking for you to draw the 3 equivalent Lewis structures for the carbonate ion. Now, if I'm not mistaken, the carbonate ion is one of those. Let me see here, hold on. Oh, it's not from the previous example. So what I'm going to do is draw the Lewis structure of the carbonate ion without going through the steps. So this is negative charge, negative charge. Okay, so this is one possible Lewis structure for the carbonate ion. And then what you can have is this pair of electrons coming here, and this pair of electrons moving up to the oxygen, and you're going to end up with this Lewis structure here. Oops, I'm messing up again. Okay, so single bond O minus single bond O minus, and then double bond O. And then now you can also have this pair of electrons, this pair of electrons coming down here, this pair of electrons moving out to the oxygen, and you're going to end up with CO minus, and a single bond here, O minus, and a double bond here, O. And that's it, all right? So those are the 3 equivalent Lewis structures, all right? And basically, it says describe how the resonance hybrid is related to the 3 structures. Basically, the resonance hybrid is, will have some characteristics of each of these 3, all right? And in fact, we can represent the hybrid by drawing this here. Let me do that here. And we use a dotted line here. And we're going to have a partial negative charge here, a partial negative charge here, and a partial negative charge here. All right, so this here is the hybrid of those 3 resonance structures, right? It's basically the structure which takes into account the other 3 individual resonance structures that you can draw on paper. Okay, so that's basically how that is done. If I remember correctly, there's one, let me see here. There's one question in this assignment which asked about that. Let me see here. Okay, so, right. Well, this is asking for resonance structures, right? So, okay. All right, let me go back to the PowerPoint here. All right, okay, some other terms I need to talk about here. Bond order and bond length. The bond order, very simple concept. It's basically the number of shared pairs of electrons in a bond, right? So a single bond would have a bond order of 1, a double bond would have a bond order of 2, and so on and so forth. So nothing too difficult about that. Now the bond length is the distance between the nuclei of 2 atoms joined by a covalent bond, right? And the bond length depends on several things, not the least of which is the particular atoms that are involved in the bond and the bond order. So some examples of different bonds shown here. So the hydrogen to hydrogen bond, what time is it? Oh. The hydrogen to hydrogen bond is of a distance of 74 picometers. For the oxygen to oxygen bond, that's 121. And you see some other values for fluorine, chlorine, and iodine, all right? What we'll be looking at in this section are some trends with respect to bond order and bond length, all right? Another term that I need to talk about here is bond energy, which is related to those as well. And the bond energy is, or also called the bond dissociation energy, is the energy required to break up the bond between two atoms in a gas phase, all right? And we met this before when we were talking about the Born-Haber cycle. So the amount of energy, for example, to break the hydrogen-hydrogen bond is 436 kilojoules, right? And in the case of water, there are two bonds. You have one bond here and one bond here. And it turns out that the amount of energy needed to break each bond in turn is different. To break the first O to H bond, it's 499 kilojoules. And then to break the other bond, it's 428 kilojoules, right? So what was done by the powers that be, some people who have a lot of time on their hands, they looked at the different values of bond energies and came up with a table which gives you the average bond energies for typical bonds. And this is the table right here, right? So this basically summarizes, and these are all average values. They're not exact or accurate, or maybe accurate, but not to a high level. These are different values for both bond length and bond dissociation energies, right? And there are certain things that you'll notice in terms of certain trends. For example, what you'll find is that when it comes to increasing of multiplicity of bond, right? If the two atoms are the same, what you'll find is that the bonds will be shorter, right? So for example, if you compare the carbon-to-carbon single bond to the carbon-to-carbon double bond to the carbon-to-carbon triple bond, look at the bond lengths, 154, 134, 120, right? So basically, the more electrons being shared between the bonds or between the atoms in the bonds, then the shorter the bond is, right? Another trend that you'll observe is that the shorter the bond, the greater the bond dissociation energy. Again, looking at carbon-to-carbon single, double, and triple bonds, you see 347 for the single bond, 611 for the double bond, and 837 for the triple bond, right? So basically, the greater the multiplicity of the bond, the shorter the bond, and the greater the bond dissociation energy, all right? And you see that not only for the carbon-to-carbon bonds, but also carbon-to-nitrogen bonds, right? You see the same trend, carbon-to-oxygen bonds, nitrogen-to-nitrogen bonds. Wherever you have multiplicity, the bonds become shorter and more energy is required to break those bonds, right? Another trend you'll observe is that if you have a situation where one atom is the same for a particular bond, but you vary the other atoms. And I'm thinking of this particular group here. Let me circle it. If you look at this particular group here, right? The only difference between those bonds is that you have chlorine, bromine, and iodine, right? Now, the thing about the chlorine, bromine, and iodine is that their atomic size increases as you go from chlorine to bromine to iodine, right? And the result is that the bond length would increase as well, as you can see, 127 to 141 to 161. And you'll notice also that in this particular case, and it's kind of weird, the bond dissociation, well, not actually weird, the bond dissociation energy decreases from 431 to 364 to 297, all right? So if you vary one atom according to size and the other atom remains fixed, as the size increases, the bond length becomes greater and the bond dissociation energy becomes less. The same is seen in this case where both atoms are the same. If you look at this group right here, right? Again, you can explain this in terms of in terms of atomic sizes. Fluorine is the smallest, followed by chlorine, followed by bromine, followed by iodine in group 7. And what do we notice here? as you go from fluorine to bromine to iodine, the bond length increases, and also you see that there's a corresponding decrease in the bond dissociation energy, with one exception right here for the chlorine. And I'll be honest with you, I'm not sure as to the reason why. All right, but generally speaking, well, actually, there are two exceptions right here. You have the chlorine and the, well, it decreases from chlorine to bromine to iodine, but for some reason there's an increase from fluorine to chlorine, and I'm not sure of the reason why. All right, okay, so that's basically the bond dissociation energies as it relates to different properties of the bond itself, and also the bond length. So what I just discussed is covered in this particular PowerPoint slide. And do we have time to discuss this? Okay, let me do a quick covering of this here. Okay, now one of the usefulness of the bond dissociation energies is that we can use it to predict what the enthalpy of a reaction would be. So here's a reaction, the reaction between nitrogen and hydrogen to form hydrazine, right? And we have the balance equation for that reaction, all right? So if you examine what's happening in this reaction, in order for the products to be formed, you first need to break the bonds between the nitrogen atoms here and the hydrogen atoms here and here, all right? And then you have the bond formation between the nitrogens and each nitrogen atom and two hydrogen atoms, right? So the bond breaking would have to take place here, here, and here. They come together, and then when the bonds are formed, energy is released, right? So what we need to do in order to calculate the energy change for this reaction is determine how much energy is expended when these bonds are broken and how much energy is released when these bonds are formed, and then find the difference between the two, and that will give you the bond dissociation energy, right? So in the case of the bond breaking, if you go back to the table I just showed you, you'll see that the amount of energy needed to break the nitrogen to nitrogen bond here, triple bond, is 946. The amount of energy needed to break each of these is 436. So you're going to add 946 plus 2 times 436, and I'm not sure what that gives. We could calculate it. Oh, it's here. Okay, my bad. So 946 plus 2 times 436, that represents the amount of energy that is expended. And then now, as far as the bonds are formed is concerned, the amount of energy expended, or I should say produced, for the nitrogen to hydrogen bonds to form is minus 389. It's negative, right? Because it's an exothermic process. The bond is being formed, and therefore energy is released. And there are 4 of those bonds. So it will be 4 times 3 times minus 389. And then we have to also take into account the nitrogen to nitrogen bond. If we look it up, the value is 163, but it must be negative because the bond is being formed. And then we find the total, right? And whatever the total is, in fact, let me do that now. So that is 946 plus 2 times 436 minus 163 plus 4 times minus 389. Okay, so according to my calculations, this works out to be equal to 99 kilojoules, right? When you do that calculation. So basically, that's the utility of determining the enthalpy the utility of the bond dissociation energy values. We can use it to determine the enthalpy change of a reaction, all right? Now, there are some limitations to this particular method of calculating delta H. And one of them, in fact, the biggest limitation is that this method of determining delta H only works well for gaseous reactions. In other words, all the reactants and products are gases, all right? So if a liquid is involved, or if the reaction is in an aqueous solution, then this is not really a good way of estimating the enthalpy change of the reaction. So a reaction like this one that we just did works well, right? Because everything involved are gases. But if there's a liquid or a solid, or if it's an aqueous solution, this will not work very well, all right? Okay, so now we're finished with this chapter. So let me just do a quick scan of the assignment here. So based on what we have covered, you should now be able to do all the questions in this chapter. Chapter 9. All right. So that's basically it for today. Yeah, so that's it. What time is it now? 1:38. Okay, so the only other thing I have to add is to remind you about the announcements I made earlier. Yeah, first, I told you guys about the test, right? No? Test number 3? Okay, so let me tell you that now. So test number 3, I will be making that available next week. Now, next week, of course, Thanksgiving starts on a Wednesday. So what I'm going to do is I'm going to submit the test to the testing center with the stipulation that it must be done between Monday of next week and Thursday of the week after the break, right? So you have the choice of doing it on Monday or Tuesday, or Monday through Thursday after the break, all right? And that test will cover okay, what did the last test cover? What chapters? Was it 6 and 7? Let me see. Okay. Actually, it's 3, 4, and 5. Okay, so test number 2 covered 3, 4, and 5. So test number 3, we'll cover 6, 7. I'm going to make it 6, 7, and 8. So what was 6 again? 6 was thermochemistry. Let me see here. Okay, 6 was thermochemistry, 7 is atomic structure, 8 was, okay, electron configuration, and so on. So let me make a note of that before I forget. Test number 3, 6, 7, and 8. Now, based on that, let me just check the, you know what, I should hide this because this will contain your grades. So can't expose your fellow students to your performance. Okay, so I have, if I'm not mistaken, I've graded and sent back to you guys assignment 6 and 7, right? Okay, so I need to grade 8 ASAP, which I have not graded yet, and send it to you guys. So I'm going to work to get that done before this week is out, among all the other things that I have to do. So look out for that. And let me see, did I post the answer keys for 6 and 7? Let me do that now if I haven't done so yet. Okay, I did publish 6, but not 7. So let me publish 7 now. Okay, so I've just published the answer key to chapter 7, assignment 7. So you can use that to help you to study. And if you have any questions, if you felt to have made any mistake in grading your stuff, please feel free to come and see me concerning that, all right? Okay, so for those of you in the lab, which would be you too, right? You saw the notice I put out, right? Well, I should have rescinded that notice because what happened was that for the lab that you're going to do today, I thought that I had left behind the information that I would need to make up a particular reagent, but I found it here. So that means that the original plan of postponing that experiment has been rescinded. So we're going to do that experiment, which is the metal ion chromatography experiment. All right. So you can head on to the lab and wait there while I get myself together. Yes, ma'am.
Tomorrow, I don't know if I did the pre-lab right, like question 200.
What was the question? I don't even have a. What is a complex ion? Okay. Draw the Lewis structure formula. Ethylene diamine tetraacetic acid, 4 minus. Well, actually, for that one, there's more than just this pair of non-bonding. Yeah, you see all these dots?
Yeah, is it all of
They're
them?
all of them are non-bonding.
Okay.
Yeah. And then let me see here, number 3. Okay, so they gave you the volume of the EDTA and the molarity, and they titrated 40 mils. Okay. So let's see here, 18. Okay, that's the moles, and then you multiply that by the molar mass, and then you divide that by the volume in liters, multiplied by a million. That looks right. I know the first part is right. Oh, okay. Divide the grams of calcium by the grams of the tap water. So this part here should be grams.
Like, how do you make it good?
Well, because they gave you the density as 1 gram per mil. So basically it's 40 mils. Okay, I knew there was something off. It should be 0.0036 divided by 40 mils times 1, which would be 40. And then you multiply by 1 million. So it would be 90 parts per million. So yeah, you didn't need to do this part. What you should have done is multiply this by 1.0 grams per mil. Then you multiply by a million. And then that gives you the final answer. All right?
So like instead of here, it's just 1 gram over 1 milliliter?
1.0 grams over 1 mil, yeah.
Okay.
Okay, let me get out of here.